And we've been talking about what makes a planet potentially habitable. The last thing we were talking about were some clarifications or elaborations on things we talked about in previous shows. One of them was, how can you find out how far away or the angular size of a star? And one of them was looking at binary stars, which are very common, eclipsing each other, getting in each other's way. If you see the two stars orbiting each other, let me use this. You can see the times that one of them gets in front of the other and reduces the total amount of light. So you have to know what the diameter of that orbit is. That's easier than finding the diameter of the star. But then you also have to know how fast that orbit is being traversed. And you can actually find out the speed of the star by watching the tiny shift in frequency of the light, the so-called Doppler effect. A little bit different from light than for sound. But basically, you're familiar with an approaching sound emitter sounding higher in pitch and then a receding one sounding lower in pitch. There's one more way that people measure the actual angular size, therefore the physical size of a star, and it's called interferometry. It makes use of the wave nature of light. It's a little complicated to explain. There are several texts, and it takes more time than we really have here. But the first test of it was by Michelson of the Michelson-Morley experiment, showing that the ether that the electromagnetic waves like light would propagate in doesn't exist. It's just bare space. Anyway, he put an elaborate apparatus on the telescope at Mount Wilson in California and measured the interference of light waves coming from the different sides of the star, basically. There's an easier way to do that now with just two moderate telescopes and what's called a high precision delay line to record the arrival of these photons at two different places. Okay, now, how about getting the separation of the planet from its star, just like our sun from us? Well, start out with something simpler. How far away is the moon from us? Again, you can use parallax, the apparent offset in view angle, when you view a distant object from two different places that are far enough apart. And that happens in our normal vision. You hold out your finger at a distance, close one eye, and then the other, and you can see the shift in what you're viewing in the background. So that works to see how far away the moon is. And the first one who tried that was Hipparchus in ancient Greece. He estimated the distance to the moon. And then Aristarchus tried to use that to get the distance to the sun. But it's really, really critical to get an exact angle. He was off pretty far. It waited until we had pretty good telescopes, and Johannes Kepler used Newton's laws to figure out how far Venus was, and then knowing how the different planets have orbits that are proportional to the 1.5 power of their distance from the sun, he could figure out how far away the Earth was. Okay, so the critical thing was, how far away is Venus from the sun? And what had to be done is to look at the so-called occultation of Venus by the sun. Critical measurements. Everybody was interested in this, historical stuff about navigation by major navies. And so the French and the English, and I'm trying to remember if others actually tried it too, they sent out expeditions, and I'm trying to remember the date, I think it was in the 1800s, to watch this rare event, the occultation Venus during a solar eclipse. And some of the ships were prevented by other ships. They were the English and the French were at war at this time, right? I think it was 1832. So some of them couldn't make the observations. Others got to their location and there were clouds. But a few did, and we got the distance to Venus, and then we knew our own distance. It was calculated, I believe, by a Frenchman, and he got 153 million kilometers. So we're at 149 million, pretty close, and we've been able to refine that since. Now, another thing I mentioned is that you have to have enough light of the right wavelengths, therefore the right energies for pushing photochemical reactions in photosynthesis. So maybe we could go over that chart again that I drew. Okay, this time I'll try to describe it better. All right. So I used the radiation laws that Max Planck and Albert Einstein and others worked out to say, okay, if you look at how much light is given off, how much energy is given off at different colors, therefore wavelengths and therefore energies, you can make a plot, which I did. And so over the range from 0, which is infinite energy, to 2 microns, 2,000 nanometers, that's going into the infrared. I made this plot, and take the middle curve that I have in this diagram. It shows the amount of radiation rising from the very long wavelengths higher and higher until it reaches a peak at around 550 nanometers, 0.55 micrometers. That's right in the center of our vision, nicely. It falls off as you go to shorter wavelengths, higher energies, into the ultraviolet. So our sun gives off about half of its total energy in the region of our vision and of our green plant photosynthesis. And on this diagram, I extended the you might say, nice region for photosynthesis to longer wavelengths, about 850 nanometers, because some bacteria do well there. So it looks comfy. There's a fair amount of energy in the ultraviolet, but we have ozone to screen us. I also drew a plot of a hot star at 12,000 Kelvin instead of our sun's 5,800, and it rises from, well, this is all relative. On an absolute scale, it's enormously higher at all wavelengths. Okay, it rises in the infrared. There's some of it in this region of vision and photosynthesis, and then as you go to short wavelengths, you get most of it, and that's all ultraviolet. That's not good for survival of anything with carbon bonds, life. I also did a plot for a very cool star, 2,000 Kelvin, the famous close-by planet, Proxima Centauri b. Well, that star is at 3,000 Kelvin, roughly. So a lot of its radiation is in the infrared, long wavelengths, and then when you get closer in at shorter wavelengths, it falls off pretty quickly. So the great majority of its radiation is in the infrared, where the energy is too low to do photochemistry with carbon-based life. So I went into some details on that earlier. We won't go into too much detail now. Now the last thing is the greenhouse effect. And where did I put that, John? Ah, there it is. Okay. The ultimate energy balance and therefore temperature of a planet is all by radiation. You've got radiation coming in from a star, our sun, for example, and some of it gets reflected, some of it gets absorbed by the planet, its surface, and that's the energy source. So if you look at our sun, well, it has 1,370 watts per meter up above the atmosphere, looking directly on it. But our planet rotates, and it's at different angles, at different latitudes. So on average, it's a fourth of that on any average part of the Earth's surface. So it's 342 watts per square meter, and about 30% of that gets reflected. So here on the surface of the Earth, it's only about 240 watts per square meter, keeping us toasty. Okay, so then how does that radiation leave? Well, the average temperature of the Earth is not what would be determined without an atmosphere. It's 390 watts per square meter. Well, that's not in balance until you realize that this greenhouse layer, which is really distributed throughout the atmosphere, absorbs a lot of that leaving thermal radiation and sends about 150 watts per square meter right back to us. Okay, so the net difference, 390 minus 150, is just that 240 watts per square meter. And that's the very simplest view of the greenhouse effect, which we are changing.